We're going to look now at one more example that illustrates a number of interesting corners in the question of optimization. Here we have a function lower, whose job is to take a string and change all of the uppercase characters into lowercase characters. So we iterate from 0 to the length of the string, checking whether something is between capital A and capital Z, and if so, making it lowercase by subtracting off the difference from the capital range to the lowercase range. This is not the way you should write this program. In something like JavaScript or Java, you might be used to writing s.length, and that works fine because in a string object, the length is immediately apparent. But in C, the strlen function has to walk down the string to find the null terminator to decide how long the string is. And by calling strlen here, it's every time around the loop, it rechecks to decide how long the string is. Right? The compiler may or may not be able to figure out that the string is not supposed to change length through this loop. So this looks like one of those classic functions that is an optimization blocker. But really, we would classify this as an algorithmic problem. Right? This is an order n operation for a string length of n. We're going around the loop n times, and so it's a quadratic program as written. And again, this is because we can write my strlen here to do exactly what string length does. It has to walk down the string to find the 0 and then return the length. So don't do that. Don't write string length in the middle part of a for loop. You should always lift it out to get the length just once, because that's almost certainly what you meant. Let's try this out, though. We're going to take lower. I'm making some big array S that has all lowercase a's in it, so I'm just computing how long it takes for lower to check that it doesn't need to do any work, really. And I'm going to try this on strings of various sizes. I'll just truncate the string to the size that I'm testing and then put the a back so that I can test an even larger version of the string. And if I do this and plot the results, then at optimization level 1, we get something like this. So the times here are running from 0 to almost 10 seconds. The size of the string, it's printed on a linear scale, but the dots get further apart because I did I multiplied the size of the string by 2 every time. The key thing is this curve is not a line. It looks like x squared, and that's exactly what we expected, right? Also, it's pretty slow. Even when we have 2 to the 18th characters only, which is not really all that big in a modern setting, it's taking 9 seconds to do the work. Now, of course, maybe we should ask the compiler to try harder, and if we ask -02, then we get a picture that looks like this. The y scale now goes from 0 to, 15 milliseconds. And the x scale actually goes further. Now we're going up to 2 to the 25th, which is would be an unusually large string. So in this case, we don't see that x squared shape. We get a linear plot out. So it's not only fast, it's also linear. And how could that be? We said that optimizing compilers don't usually change the algorithmic complexity. In this case, it really has. If we look at this program and decompile it, right, then we had, we're going to do a comparison and change the string, and then maybe change the string, and then call strlen again to see whether we should keep going. In the C code, though, the strlen call is just before we recur, right? That's as expected. But when we do the comparison, we jump down to label 10. We jump over that. And that's because the compiler actually knows about strlen. It knows that strlen of an s that doesn't change will be a constant, and it knows if the character we looked at did not cause us to change the string, then it can skip over the strlen call. So this is frankly a little bit surprising, but it's a result of the compiler having string length as a special case. If we change our program so that we use capital A's instead of lowercase a's, then that will cause our lower function to keep changing the string, and based on what we looked at the machine code, we should expect it to call strlen many times. And in fact, that's what happened. So still with GCC-02, but using capital A's instead of lowercase, we're back to the slow world, where our y scale now is going to 11 seconds. Our x scale is still bigger than it was than the -01 case, but the point is that we have a quadratic curve here, as expected. So the optimizer did change the complexity of this program, the asymptotic complexity, but only in some cases, not in all cases. We can also see if we go back to lowercase a's and we use my strlen, which was completely equivalent to strlen what it does, that we get the quadratic behavior that we originally expected, and that's because the compiler can't figure out that my strlen is exactly equivalent to strlen. It doesn't know that it's going to be a constant, and then it can do some special cases when the input string doesn't change. Right? So the conclusions there are, first, don't use the bad algorithm in the first place. All of these problems are solved and avoided by getting the length of the string just once before looping over it. But the other thing is to not be surprised when using a standard function gives you better or different results than you might expect from a generic function or some function that you wrote, like my strlen.